Hello, folks. How's everybody doing? I hope you're doing fine. I'm doing okay for now, I guess. I'm going to be answering some questions today, so if you have any, let me know. And the other thing I want to let you know is that I'm going to be on the road this week, so I probably won't have the next lecture until next Sunday. Okay, keep that in mind. Okay, I'm going to start where I left off the other day, and that's some of the problems we have with particles serving as mediators for gravity. Okay, and these are the problems that I find, among others. Right, this is like a synthesis, right? Summary. Um, they have irrational mechanisms for gravity, no matter how you look at it. They have to explain pull, and the way they do it is in a Ptolemaic, irrational way. They have to go out of their way to produce pull through push. Okay, and it's kind of comical in the end, because you wonder why they have to go through all this pain when they can just say, well, what if gravity is a pull force and not a push force? Okay, and one of the problems is direction. Right there, you see it, direction. What's the problem with direction? Well, here's a couple issues. You got people standing all over the earth, okay? You got people in China, in Russia, in Africa, in South America, North America, Europe. And we know, or those who believe in the globular earth, that our feet are all pointed towards the center of the earth. That's in fact the official explanation, okay? So the question is, why does gravity have that direction? Why is everything pointing towards the center of the Earth? How would you explain this with particles? That's the issue, okay? And under the rope model, very simple. We're all tied. Every atom in our body is tied to every atom in all that comprises the Earth. Every atom of my body is bound to every atom in your body, right through the center of the earth, or through the edge of the earth, or through whatever. All atoms are interconnected. That's the theory, or that's the proposal. That's the assumption. And with that, you can explain direction. Okay, why we are tied, because we're all bound to towards the center of the earth, because as you approach the earth, um, it's like a cobweb. The center of the cobweb is the center where all the cobwebs meet. So, and that's essentially the best explanation for that. It's just a visual explanation. We can explain direction very easily. Okay, and then what's the hold it? Yeah, let me get myself back in here. And then the other issue is how gravity goes through things. There's three issues. The last three issues are more or less um, related to each other. Okay, how gravity goes through things without pushing them. Okay, how gravity acts um, both ways, both directions. Remember, the particles have to go through you and come back also, because they're coming from some other part of the universe. Okay, and then the shielding effect, masking effect. You're at home and you jump, and if you were to measure that, very precisely, you accelerate towards the Earth at 9.8 meters per second square. Now try it in the yard. You know, underneath the sun, underneath the sky, and you'll find that you accelerate at exactly the same rate. And how can that possibly be when inside your house you're covered and outside you're not? I mean, how can you explain that with particles? And that comes back to those other 2 points. You have to have it both ways. Particles have to go through your house, through the roof of your house to reach you, and at the same time, they have to push on the house. Okay? So it's got to do both. See, if you cover your head with an umbrella, right? Gravity has to do two things. It has to push the umbrella and you, and it also has to go through the umbrella to push on you. Okay, so this is the issue. The issue is that if you're inside your house, you would think the roof stops whatever rain comes down, right? And then you would be liberated from gravity. You say, "Oh, fortunately, we don't have all those gravity particles pushing down on my shoulders because I have a roof over my head." It's not the case. Okay? It's not the case. Gravity goes through things, and until you understand it and are able to answer those kinds of questions, you have not, got a handle on gravity, on the theory of gravity. Okay, so let's continue here. I explained or illustrated last week what the problems of particles are. Okay, and here's one. You have this is how quantum explains gravity. Essentially, it says that one object casts or throws negative momentum particles at another object. That's how it attracts it. That's how the mathematicians explain attraction at a distance. They say it sends negative momentum particles, or the particles deliver negative momentum, negative motion. Okay, so I had to ridicule them with this little illustration because that's the mechanism they propose. So keep that in mind. The point here is that this is the mechanism they propose, and if we applied that to the solar system, like to the Earth, the orbit of the Earth, you would get something like this, okay, where the sun would throw particles at the Earth, and those particles carry negative momentum. They deliver negative motion and prevent the Earth from flying out of the solar system. Now, quantum doesn't apply to the cosmic scenario. Okay, they're clear on that. But essentially, quantum doesn't have a gravitational theory. Whether here on Earth or out there in space, it has no gravitational theory. That's the big problem with quantum mechanics. But if we applied the mechanism that quantum mechanics proposes to the cosmic scenario, to the Earth, the orbit of the Earth, this is what you would get. The particles would, the sun would throw particles at the Earth, and those particles carry negative momentum. That's how they do it, with a little negative sign in the equation, and the Earth doesn't fly away. That's essentially the theory. Okay, so that's what they're proposing, not for the solar system, not for even for gravity at all. This is the mechanism that quantum has for uh, attraction. Whenever they have to explain attraction, they just put a negative sign. What is that negative sign? Negative momentum. That's what the main body is transferring to whatever other body that it attracts from a distance. So it's up to you to, whether you think that's a rational explanation. That's the story. Okay. Okay. Is that the only one? No, there's another version that's known as Lesage or Casimir type effects, where rather than throw negative stones from the front at you, the mechanism here is they remove whatever separates you two, and particles from behind push both of you together. So if you want to come close to your car, you remove the particles or the air, whatever separates you from you and the car, whatever's between you two, and supposedly the particles from outside the car and outside you push the car and you together. That's the other mechanism of attraction. Here I again ridicule it. That's how you attract a donkey. You just remove particles from between you, and particles from the outside push you together. That's the Lesage notion, the Casimir effect, okay, type of mechanism. And this is what a lot of particle theorists propose, okay? So they propose this kind of mechanism, okay? The reason I ridicule it with the donkey is for you to drive home the point that this is what they're saying. This is what they're proposing. They're proposing not for donkeys. I'm sure they would use a rope to pull on a donkey, right? But this is what they're proposing when they go into attraction. When they say action at a distant attraction, well, how does that happen? Well, let me show you. And this is the type of mechanisms they propose. In one case, negative momentum transfers. The stones that they throw at you have negative motion. In the other case, they will remove whatever's between you and the object you're trying to pull, and the forces of evil on the outside push you together. That's it. And so it's up to you to whether these mechanisms are viable. I mean, is this rational to you? That's what you got to put in your mind. Isn't it better to say, action at a distance is done with pull? And yeah, that's been the problem. No one has ever figured out pull. Push is easy, especially with particles. Everybody's been doing pressure, pull, push, particles for as long as we can remember, because everybody can imagine, pushing a box. Okay. And on the other hand, it's much easier to say, what if there's something between you and the box? I mean, you would think this is a much more rational or what is it, William of Ockham way of doing things. Just choose the simplest mechanism. By God. Now, one of the things you got to keep in mind, and I do always want to rub this one in, you got Richard Muller. He's a professor at Berkeley, mathematical physics. But it's important to understand what he's saying, because if you can understand what he's saying, you got half the battle won. Okay, you got half the battle won. So it's important. Just listen to what this guy is saying, because he's giving you a description of gravity, what you have to explain if you have a gravitational theory. If you want to propose a gravitational theory, whatever you want to propose, it doesn't matter. This is what you got to answer. Okay, keep this in your mind. Try to imprint it in your mind, because this is what you got to answer, and I'll tell you why in a second. But first, let's find out what he's proposing. Okay, this is what he's saying. Richard Muller says that you have to explain the following. You have your little mass here and the big mass. The big mass is the Earth. He drew it on the board. And little mass is that little man standing on the Earth. Okay, and he says every atom on Earth is pulling on every atom of you. You're also pulling on it. That's the first thing you have to explain if you want to propose a gravitational theory. You must explain that phenomenon, that description. Every atom on Earth is pulling on every atom of you. You're also pulling on it. The other one is the last statement there. He says the amazing thing about gravity is that it goes right through things. So how can you push on a particle while going through it? This is what you got to explain, and it's painful for the particle proponent, because he's got to reconcile those two statements. He's got to show how on the one hand you're pushing, and on the other one you're also pulling right through it, or going right through it. And it's difficult for people to understand what you got to explain. That's why I try to rub it in and make sure that you understand. You have to explain two things. How every atom on Earth is pulling on every atom of you. You want to do it with particles? Fine. How is it possible that every atom on Earth is somehow, how is it possible that you're attracted to every atom on Earth? Okay? That means every atom in your body is being attracted by every atom on Earth. How do you do that with particles? Okay, that's the first issue. The second issue is that gravity goes right through things. So if you have a particle theory, the particle has to go through you and also push on you. I don't know if I'm getting myself, if you understand what I'm trying to get here. And I've illustrated this, okay? And here it is. Okay, here's the illustration. Okay, here's you jumping on Earth, okay? And you got all the particles coming from every part of the universe. They're also coming underneath the ground through the Earth, because remember, gravity goes through things, and you have particles from the other side of the universe that's underneath the Earth at that point, under that, picture. Okay, so particles are going right through everything. Okay, that's the first issue. The second issue is that, if you jump at home, it's going to be the same thing as if you jump in your yard without a house. So here you have a roof, okay, and here you don't. And whatever the case, your acceleration towards the center of the earth is the same, whether you are protected or not. You cannot protect yourself. You cannot shield yourself from gravity. Gravity goes right through things, right through your walls. You got to take a step back and think about that. How do you explain such a phenomenon? And again, no one has been able to. That's the point. In the case of relativity, they say warp space time, right? But even that doesn't work. I mean, the three-body system doesn't work. You can't do it with sun, moon, and uh, sun, earth, and moon, because that same mechanism you cannot translate it or extrapolate it to Uranus, Oberon, and the Sun, or Charon, Pluto, and the Sun, because they would all have to push the canvas downwards. And that's not the case, because the rotation of the moons, of those moons, Oberon goes over the North Pole of towards the Sun in the case of Uranus. And in the case of Pluto and Charon, it's like a bullseye pattern as seen from the Sun. It's sideways. So for that to be sideways, Pluto would have to push the canvas outwards. But why would it push it outwards if the Sun is pushing it downwards, requiring Pluto to go around, downwards? So you can't extrapolate it to a three-body system. You cannot even simulate it in the lab. So they just do equations, say, well, this is what we gather from our equations, but they have no way of illustrating, a three-body system. And you'll always see space-time warpage being done with a two-body system. Ask them to do it with a three-body system. There's one guy there who, on the internet and on YouTube, who has this bowling ball or something, has this curvature, and he shows people how the ball goes around. Ask that same guy to do it with a three-body system. Let's see if he can do the same thing. And that's where he fails. And yeah, you can't do it. And anyways, gravity goes through walls. This is what you got to explain. An atom shoots to another atom right through the wall. In fact, the atom is also attracting the atoms of the wall, for that matter. So it's got to go through and at the same time attract. And what's the problem with that? Let's see. Yeah, here it is. Here's the illustration. If you got six atoms there on the wall, sideways wall, and the particles of gravity that you are going to propose, they have to go right through the wall. They have to go right through the atoms. And if the atoms are all aligned at a given point, each one of those atoms pulls on the one next to it. Keep that in mind first. Every atom pulls on every atom. That's what the description is. And then the particles that come from outer space, gravity particles, they have to go through all of them. And at the same time, go through and push. You're going to have a hard time doing this with particles, no matter how you look at it. And that's why nobody has. Nobody in the last 10,000 years have been able to solve gravity, because those are the issues that they could not resolve. But with every atom being interconnected, hey, we can explain why every atom pulls on you and why gravity goes through things. We explain those two things that particles cannot explain. Okay. But today I wanted to talk a little bit about a change that's happened. That's the paradigm change. Okay. And that came from this gentleman. His name was Thomas Kuhn. Okay. And give me a second here. I lost my I moved something out of place and it's no longer there now. See if I can get it back. No, I won't be able to. Well, anyways, I'll just summarize. Kuhn said that there are changes throughout history, and there are revolutions. There are um, revolutions in thought. Okay, and those revolutions in thought carry an entire generation. That means that at some point there's a change, and that change, as always, starts with one person. Okay, it has to start with one person. He doesn't address that issue, but what he addresses is the fact that there are phases to it. The first phase is that everybody has different ideas about something. Okay, and so it's like a scattered paradigm where everybody has their own paradigm. There are different clubs, different associations. This guy thinks this. This other guy thinks that. That's the first. That's like the first step. Well, what happens? You try, and in the scientific world, that's what we're going to relate to. The next step, you have to zero in on certain problems. You come across certain problems, you try to solve them, okay? And you can solve several problems with your paradigm, with your notion, with your theory, with your assumptions. But it comes a point where where you run into a brick wall and you cannot explain something, and that's when people start talking, arguing, and obviously someone else comes in and says, I got a different idea. I got a different proposal. Okay? And so he starts the ball rolling. And the first reaction of the old guard is to say, no, no, this guy's an idiot. He's a crank. He's a conspiracist. You get all these labels. He gets thrown out. He's the guy who doesn't have an army behind him. Right? He's a lonely guy. And other people pick up on that and say, well, this guy's right. I mean, I like his idea better than you guys. And slowly this generation dies, and the new generation pops up with a new paradigm. Okay, and the thing repeats itself. Now these guys run into troubles, right? They reach a moment of crisis, more where crises become continuous. They run it with a problem here, another problem there, another problem there, and they can't solve it with a paradigm, and so now they have to invent something new. And a new guy comes into the picture, the new kid in town. He comes in with a new idea. Again, he's a lonely guy. Again, he's trampled by the old guard. Okay, and so on down the line. And yeah, what I wanted to show you today is that we had a little bit of that throughout history. And I'll just go relatively quickly through it, but I just want you to see what happened here. We started more or less with the Greeks. That's where we get our overall ideas. Okay, we had Thales. He proposed water was the ultimate thing that underlay everything. Okay, all the matter in the universe. It all eventually came down to water, according to him. And Anaximander, he said, no, it's air, earth, air, uh, fire, hot, cold, wet, dry. He had these, opposites, right? And these folks, Anaxagoras was one of his um, students of Anaximenes, and they came up with a flat Earth, among other things. But the important thing is that in this context is that Anaximenes said, look, the ultimate um, element is air. It's not water. It's air, and different densities of air created fire, air, wind, cloud, water, etc., and earth and the stones. Okay, Plato mentions that. Heraclitus, he said, no, it's fire. It's not water. It's not air. It's fire. Okay, Parmenides, he just said, no, it's, again, opposites. Day and night, Day and night, you are the one. Okay. Anyways, Leucippus and Democritus, they say, no, you guys are all wrong. It's atoms and empty space. That's all there is, you know. And Empedocles, he came up with the four elements. He got that, I think, from the East. I don't think that was his original thought. And Plato and Aristotle added the ether, even though that already came from Hesiod. Hesiod was 7th century BC. He wrote about the gods, and he talked about ether, one of the gods, right? And ether essentially means burnt air, and it was what the gods breathed. Okay, we didn't breathe. So the way Plato and Aristotle looked at this is, that's not here on Earth. That's out there in the world of the gods. They breathe that stuff. We never get a chance to see that. But the ether is what people eventually used from that point on, all the way to the 17th century and even beyond. As I'm going to show in a second here. Okay, that was our starting point. That's when all the original ideas, you could say, came up. When people started wondering, what is matter? What is motion? What are things made of? You know, and and so we ended up in the 17th century. Essentially, not much happened in between. A lot of people just quoted Aristotle, and he was taken as truth, as law. And then we arrive at the 17th century when people started asking questions. I call it the age of ether because ether again came into prominence, especially in regards to light. Okay, and they began to explain everything in terms of ether. We had the invention of the calculus by Newton and Leibniz. Torricelli, von Guericke, and Boyle, they ran experiments on vacuum, and they believed that they created a vacuum. And Descartes and Hobbes, Thomas Hobbes, among others, right? I'm just mentioning a couple snapshots here. Uh, they didn't believe that you could ever have a true vacuum, that there is no such thing as nothing. Okay, kind of weird, no such thing as nothing. Okay, they didn't believe that there was a vacuum out there, that everything had something in it. What they never asked, which is the question I would ask them, is what surrounds each particle? I mean, if each little particle has shape, each little particle of ether has shape, what surrounds, what gives contour to each particle? What is the backdrop? More particles? Well, at some point, you're going to have to answer what separates one particle from another. Why does it have shape? Why does it have a surface? What is the backdrop to that? What are we going to call that medium or whatever you want to call it? So that's the question I would ask them, and I think that's a failure in just straightforward reasoning. You don't have to have any math, that's something anyone can understand. What is the backdrop? That's all I'm asking. What separates one surface from another? Okay, Hooke and Huygens. Robert Hooke was really the guy who came up with the notion of the wave. Okay, in his famous treatise. And they believe that light is some kind of vibration of the ether. Newton said, no, it's not the ether that vibrates, it's these particles, these corpuscles that go through the ether. Okay? That was the notions they had. Okay, so they were trying to explain light primarily. So that was the starting point where they threw fuel into the fire, right, for ether. And ether from there just took off. And again, it was no longer of the gods. Now it was everywhere. Okay, now it was here on Earth. We had the ether here on Earth. Okay, in the 18th century, not much happened except, it was, you can call it the age of experiments. They started experimenting, and it was the dawn of electricity. They started playing around with the Leyden jar, which gave them a shock. They loved that. You had Ben Franklin with a key, with the kite, right? Coulomb, he came up with the torsion balance. He came up with a relation that was very similar to Newton's gravitational, mass divided distance square. Well, he had charge. Okay. Volta, he came up with a pile, okay, with a battery. Okay, and that started to be used extensively in different countries. And towards the end of the century, Cavendish does his torsion balance experiment in regards to gravity and comes up with a gravitational constant G. That's about it. Nobody had any idea up to this point what gravity was. What is gravity? Why when I jump I fall back to Earth? Nobody had any explanation for gravity, and it was just like, oh, that's interesting, and that was it. I didn't get past that. Light was the issue, and in the 18th century, I think they loved this newfound thing called electricity. They really started to play around with electricity. 19th century, I would say, you could say it's the second age of ether. Ether took off once more, Again, in relation to light, they were trying to explain light. What is light? That was the question. Okay, forget about gravity. Nobody even touched gravity. Okay, you can see that it's all light, and they ended up with little by little they were approaching at least the beginning of the planetary atom. Okay, they had the Thomson's plum pudding model, you know, but that at the turn of the century that died relatively quickly into the 20th century, and what took off was the planetary model. Okay, and that's the one we have today, by the way. People will say, well, no, that's not the planetary model. If you look it up, you just Google atom in images for Google or any other browser, and what you'll find is the pictures of what everybody thinks an atom is, and it's the planetary model, which was developed by Rutherford and Bohr. Okay. Anyways, they abandoned the longitudinal wave, which was essentially what Huygens was proposing, and as a mediator for light, right? And they went with Fresnel's transverse wave. Okay, that started relatively early in the 19th century. Okay, and again, no idea what gravity is. Faraday, he did a lot of experiments and he presented them at the Royal Society, but he had no idea what he was doing. All he did was describe. He said, "Look, this is what I saw in the lab." So he would do experiments. He would even do the experiments in the Royal Society. He would do the experiments there in front of a crowd, but he had no explanation. And he just invented words like field. He's the guy who invented the word field, okay, that we still use today, that incredible four-letter word, okay, field. And he had no explanation. And neither did any of the others, Maxwell, who also described it mathematically. But again, he had no explanation for this, because if you look at the transverse wave that is still in vogue today, which people still use today, just look at it. You know, you see this thing moving and you say, okay, the magnetic field, the electric field. What you're staring at is a bunch of vectors, magnitude and direction. That's what each one of those little arrows or those little extensions for the electric field and magnetic field represent. It's just vectors. What they're showing you is a mathematical concept that is in motion. That's what you're staring at. There is no physical object called wave. They just have no other way of presenting it. They say, look, just think of it this way. The values go up and down. That's why, you know, the values oscillate. And they're looking at values only. They're saying there's something there. We don't know what it is. We don't care anymore. But all we're saying is the values increase and decrease. That's all you're staring at. And it moves forward because light moves forward. So they had to represent it somehow. And that's what they came up with this transverse wave that you see typically, you know, moving across the screen. Okay. Michelson and Morley, well, they finally decided by the way, the whole century, 19th century was a century of ether. Everybody just talked about the ether and that light was a vibration of the ether. They were thinking of waves. They did away with Newton particles going through the ether. They said, no, that's not the case. It's the ether that's vibrating. And then Michelson and Morley, supposedly, because there are different opinions on this, okay, you just got to read quite a bit. There's different interpretations of what Michelson and Morley really proved or discovered or whatever. But the consensus of the mathematical physicists who came out in the 20th century and from there onwards was that Michelson and Morley proved the non-existence of the ether. There was no ether, okay? And towards the end of the century, they developed cathode rays, electron. They discovered the electron, or they thought the electron had a negative charge. They assigned a negative charge to the electron arbitrarily. It's Thomson who's going to figure out that the electron is part of the atom. So now you're starting to see this planetary model arise, and it's going to take off, at the turn of the century into the 20th century, right? Okay, so here's the 20th century. Okay, here again, as you can see, paradigm is changing, different notions that people have. 20th century is the dawn of abstraction, it's the dawn of irrationality. They start giving irrational physical interpretation. No longer do you have a rational physical interpretation. What do I mean by that? I mean that now you're using concepts as objects. You're going to transfer energy. What do you mean transfer energy is a concept, mathematical concept? Now you're going to move a mass. What do you mean you're going to move a mass? Mass is a physical object. What does it look like? You're going to extend a field. What do you mean extend a field? Field is a concept. It's a region of values. And so on and on. Charge is a concept. It's a value. And people don't realize, they think they say, oh, I moved a charge, or the electricity is the flow of charges. It can't be the flow of charges because there's no physical object called a charge. People don't realize we got so brainwashed with the language in high school and in college that we use it and we don't even realize it. But when you analyze it, you say there is no physical object called charge, no physical object called mass, energy, field, time. They warp time, Okay, so the quantum particle replaces the real corpuscle. Quantum particle is a vibration of whatever. It's all verb and no noun. Okay? That's what you got to keep in the back of your mind. Space-time replaces the ether. They said, well, the ether doesn't exist. What does exist? And they said, well, it's space-time. What is space-time? Well, it's a mathematical concept. So now we have space and time, minutes and seconds together with lengths, meters and yards. We blend them together. We blend the second with the meter, and we get space-time. So why do I say that? We have irrational physical interpretation. We have abstractions. Yeah, it's all nonsense. You can't understand it from a rational point of view, from a mechanistic point of view. You can only understand it from a mathematical point of view. Say, look, here's the equation. I can understand this. I can understand the relations. But you cannot go to the lab and say, let me show you. Because what are you going to show? What are you going to show for space-time? And of course, they had to put it beyond your brain and say, well, space-time is unimaginable because it's four-dimensional. Okay? The photon, 0D and massless. The black hole, 0D and infinite mass. You got all these. Then you have dark matter, conveniently heavy and invisible, and so on down the line. It's all irrational. You cannot visualize anything. People want to see. People say, tell me how. I don't want to know all that nonsense. I want to know why I'm falling to the center of the earth. Why when I throw myself with my parachute from the airplane, why am I drawn to the center of the earth? Why am I afraid of heights if I can fly maybe, like Superman or like an eagle? No, you're going to fall. You just drop yourself from the mountain, you're going to go way down. You know this. Even some animals know this. So the question is, you want to know those answers. You want to know, why are you falling towards the center of the earth? And they cannot tell you this. They can say, well, let me explain to you. You have negative momentum transfer, you have Casimir type effects, and you have bent space-time. Now, which do you like? Okay. So yeah, the problem is they use concepts as objects. You have field, energy, mass, time, charge. That's the big problem. And you say, well, Bill, that's your interpretation. Well, let's bring authority to bear, okay, so that you don't believe little old me, okay? Don't believe me. I tell lies. I went to prison. I work with the CIA, right? So let's get some real authorities here, okay? And here you have Mr. Richard Feynman. He said, I think I can safely say that nobody understands quantum mechanics. Okay? Do not keep asking yourself if you can possibly avoid it. But how can it be like that? Nobody knows how it can be like that. The more you see how strangely nature behaves, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics has given up on that. They have given up on that. Okay? They don't do physical interpretations anymore. They consider those things to be, how shall we say, philosophy. So if you ask a question a question involving mechanisms, qualitative stuff, that doesn't involve numbers, that doesn't involve quantities, measurement, descriptions. If you want an explanation of a mechanism, they just tell you you're in the wrong campus. You got to go to the other side where the philosophers are. Okay, so you go to the philosopher side of the campus and you ask them. It turns out the philosophers, you go to the Stanford um, uh, what is it, dictionary, what is it, encyclopedia of philosophy. They do mathematical physics. They do the same thing. They get their cues from mathematical physicists. So they're interpreting all the stuff that comes out of mathematical physics and try to interpret it from a qualitative perspective. And it's all irrational as well. You won't find anything rational on either side of campus because they're all in the same boat. These guys do math and physical interpretation. When you ask them about how irrational their physical interpretation is, they say, go to the other side of campus. We don't do opinions. We don't do uh, philosophy, which is what you're asking. That's on the other side. You go to the other side and say, oh, yeah, we just got our information from the mathematical physicists, and we just go with their physical interpretation. So there is no one you can check today, an authoritative figure out there that you can consult on the formal physical interpretation of the equations. It's all irrational. That's why, when you realize that and you say, well, am I the only guy on earth? No, a lot of people realize this already. It's irrational. It's that it's not part of the subject matter anymore. That's the problem. It's no longer subject matter discussed in mathematical physics. Okay. Okay. So what do we propose instead? Well, let's see if we can get it here. Where is it? Oh, well, I had another comment here, just in case, moral authority. Here you have Leo Susskind. He's a professor at Stanford. And he says, you and I evolved in a world of 3 dimensions. We can't visualize more dimensions. I can visualize 3 dimensions in my head, but I use X, Y, and Z to describe them mathematically. Now I go to 4 dimensions or 5 dimensions. I can't visualize them anymore. I can't say now, close your eyes and view in your head 5 dimensions because I can't do it either. So we're stuck needing mathematics because evolution didn't equip us to be able to visualize quantum mechanics. It didn't equip us to visualize 11-dimensional spacetimes. Evolution did this to us. That's the answer you get. Okay, so you're not going to get a qualitative answer for anything. And I'm saying absolutely anything. I mean, all the invisible phenomena, light, gravity, magnetism, electricity, the workings of the atom, uh, black hole phenomena. How is it that our star revolves around nothing, orbits around nothing very fast? How is it that it loses its skin to whatever's out there, the mass in the universe, the invisible mass? What is dark matter? How is it that the stars on the outside of a galaxy don't go flying out? What keeps them tied to the galaxy? Why do they rotate faster than the ones on the inside? They have no explanations for anything. It's all irrational. It's all done with mass, and mass is a concept. You can't say kilograms did this and kilograms did that. I mean, how does a kilogram pull on a star? That's what you got to ask. They say it's the mass, right? Okay, it's the mass. Mass is kilograms. How does a kilogram pull on a star and force it to go around? That's what you see. It's all a description. They say, well, if you have so much kilograms here, this is the effect it would produce. That's what they're saying. Well, can we see those kilograms with the elephant that's in there that's pulling on the little ant around it? No, you can't see it because it's conveniently dark. You can only see it through equations. That's the issue. Okay, that's what's happening. Okay, so what is it that we crossed the Rubicon, right? And now we have a new paradigm for the 21st century. And this is what we have, okay? So for those of you who are interested in new ideas, doesn't mean you're going to believe them. It just means it's going to tickle your curiosity. That's all we're saying here, okay? And so, what we're saying is this is the age of interconnectedness or interconnection. It's the dawn of the rope model, okay? Rope hypothesis. We're abandoning irrational mathematical physics mechanisms. We have rational physical mechanisms. We are introducing the force of pull for the first time in history. Everybody's been doing push all this time. We're doing pull for the first time on Earth. Okay. Atoms are all physically interconnected. Now we explain gravity because every atom on Earth is pulling on you and it's going right through that atom to the next atom to the next atom to the next atom. It's pulling on every atom in the row because they're all aligned on the same axis. Okay, um, and there's simple explanations for all invisible mechanisms. And I'm saying that what we're giving is mechanisms. Okay, so you're going to see a mechanism. It's going to be a movie. You're going to watch the movie and say, okay, I understand the mechanism. Hopefully, because by watching the movie, you say, okay, I understand what he's proposing. Doesn't mean you believe it. No, we don't care about that. Belief has to do with religion, with opinion. We just care that you understand the mechanism. What we're saying, all these people are wrong in the sense that they're saying, well, we'll never be able to explain gravity. We'll never be able to explain light. We'll never, all these invisible things, we'll never be able to explain them because they're outside of human sensory experience. And what they're saying is, yeah, you can't touch light. You can't taste light. You can't smell it. You can't hear it. So what do? We say, well, there's no way to prove it in the lab. Of course not. Mother Nature was smart. She said, look, we better make these things intangible and invisible because otherwise, we're all going to be tangled in all this stuff, right? Or we're going to bump into things if they're not intangible and invisible. And so what we're saying is, yes, you do not prove the existence of these things in the lab by running some kind of experiment that exposes the physical nature of the invisible, intangible mediators that Mother Nature uses to run her shop. Okay? And we're saying it's the death of the particle. Okay? Okay, I'm going to see if we have some questions. And let's see if anyone has come up with any questions here. So give me a second here. I'm just going to go through, see if I can see any decent questions here. Give me a second. Let me get this here first out of there. Okay, let's see. Is gravity needed only to explain the so-called planets and stars? And other light phenomena up there. Well, I don't know about light phenomena, but you do need gravity to explain something very simple, really. The question is, can you explain why the Earth doesn't fly out of the solar system? Very simple question. And it should pique your curiosity if you're interested in in how this universe works. You may not even be interested in physics at the very fine level, but you have to explain why a planet doesn't fly away. I mean, what keeps Mercury rolling around the sun or Pluto rolling around the sun? I think people want to know these basic questions from a qualitative standpoint. And if the guy gives you an answer, says, well, it's warp space or space time. And what is this space time? Well, you can't imagine it because it's 4-dimensional, we're 3-dimensional beings, and that's the explanation he gives you. Well, I don't know. It's up to you to see if if you're going to accept that as a valid explanation. Okay, so I think what we need to answer here is why don't planets run out of the solar system? That's just a basic question that I think a lot of people want to know, and I'm saying very simple. In fact, I don't think I have it now. Let's see if I have it here. No. But you can twirl a ball around your head, at the end of a string. I've got one of those. I kind of lost it right now. I always had it here. You swing a ball around the end of a string, and you'll find out why that ball doesn't fly away. It's because it's tied to the string, which is tied to your hand. If your hand is the sun and the ball is the earth, well, you can swing around forever. Okay, so that's essentially the mechanism. Very simple kindergartenish mechanism. Mother Nature cannot be that sophisticated. Okay, keep in mind one thing. What's out there? What's out there? Rocks. What you have is Venus, Mercury, Earth, Mars. These are rocks. Then you have some gas balls. Uranus, Jupiter, Saturn, right? And obviously the sun, another bigger gas ball. Now, how difficult is that? Now, think about that for a second. You have a little fireball and you have a little rock. That's it. That's all there is. How difficult can it be, the mechanism, to prevent that rock from flying away from the big ball of fire? You got to explain a mechanism. And the question is, are you going to push from the outside? Are you going to warp space? Are you going to throw negative momentum stones at it? Or are you just going to tie a rope from the sun to the earth? Which do you think is the more rational or the most Occam-like, the simplest explanation? At least that one explains it straightforward. Everybody can understand it. It doesn't mean you're going to believe it. It doesn't mean you're going to say, well, I don't see a rope. I don't see, okay, fine. You can say anything you want. My point is that you will understand the mechanism that's being proposed. Oh, I went blurry. Hopefully it's not the wine that went to my head. Okay, so my point here is that we're talking about mechanisms, about physical mechanisms, about qualitative stuff, okay? And yeah, all you want to know is a mechanism so that you can understand it. Say, okay, I understand that one, okay? Can you understand the others? Do they make sense to you? Okay? So that's where you can compare some of these things. Okay, let's see, we got another question here. Let me look, give me a second. Here, someone says, Gary from Draft Physics has a good particle model of gravity. Well, yeah, it'd be nice if this individual can put a, can make a can illustrate, can make a movie of it. Okay, that'd be great. We would love to see what kind of movie he does, and if he answers all the questions that I just presented. Okay, in other words, you have to explain how the particles go through and also push. He's got to explain that. And a lot of these people, what they do is they begin by denying that that's what gravity does. They have to do that because they have no way of explaining it. So they'll say, that's not true. Okay, so they start by denying what is, and therefore they can say, now let me explain my theory to you. And what they do is they just explain it and they never show a movie of it. So the issue is they have to show a movie like I did here, showing how particles go through and at the same time push. That's gravity. If you cannot answer that question, your particle theory is worthless. Okay, and that's why nobody in officialdom, in the official world of mathematical physics, pays any attention to any of these dissidents. You have to keep in mind that the mathematical physicists have abandoned the real particle hypothesis. That's the paradigm shifted in the 20th century. What shifted was they no longer deal with real particles. A lot of people don't know that. They keep drawing the little ball and they say, look, this is a photon. No, that's okay for pictorial representation of trying to explain to someone, what you're talking about, your mechanism. But you cannot believe that you're dealing with real particles anymore. Mathematical physics in its entirety has abandoned the physical particle, the corpuscle. They're doing it with concepts. The particle is not a particle, it's not a little ball. And all these dissidents, they're still 10 steps behind quantum because all these people are trying to do it with real particles. You can't do gravity with real particles because you have to explain how it goes through an object and at the same time pushes it. Good luck. So yeah, it can't be a very intelligent individual who still proposes particles. It means he's either very ignorant of what he's got to show or he's deluded. He's got a mental problem. Okay, there is no other alternative. Okay, let's see if we got any other questions here. Are you saying vacuum does not exist? Well, that's a big question because the first thing you got to answer there is, what does the word exist mean? That's a big one. Okay, nobody has ever defined it, and physics is the science of existence. Physics only studies that which exists. So you do have to answer, you have to define the word exist. That's the first one. And you cannot say a concept exists, not in physics, not in science. That's okay in ordinary speech, okay? It has to be an object in order to exist. And if the vacuum is not an object, you cannot say, does the vacuum exist? That's an irrational statement. It's like saying, does love exist? That's in ordinary speech. That's in poetry, not in science. You can't say love exists in science. Okay? God has to choose whether he's an object or a concept. If God is a concept, he cannot exist by definition. And if he's an object, that's not sufficient. He's got to have also location. Okay, so that's the first one. So you cannot say the vacuum exists. You cannot say space exists. That's an irrational statement, okay, for science. And so the language is crucial here. Okay, let's see what else we have. Vacuum is what is between surfaces of matter. No, vacuum, the definition of vacuum is that which has no shape. That's the definition of vacuum. That's the definition of space. That's the definition of nothing. Okay? That which has no shape. An object is that which has shape. Okay? And nothing is that which doesn't have shape. So now we can use these words consistently. We can say, what is something? That which has shape. What is nothing? That which doesn't have shape. And something is an antonym of nothing, so we can use the words consistently. But if you say, well, that's what we find between two objects. Well, I can find another object between two objects. So does that make that center object nothing? So you got to be careful with definitions, because you got to set the foundations in order to talk intelligently. Okay, and that's what one of the things you got to do. You got to define your terms. And I'm saying, something is that which has shape, nothing is that which doesn't have shape. Now, these are antonyms. You can use them consistently. Now you can talk straightforward, and people can follow your presentation. Okay, let's see what else we got here. Okay, one guy says, Olaf says apples and bananas equal space-time. Deny it and you're a crank. Okay. Okay, what's the question? Someone says, let's see what he said. You mentioned in the past shows electricity cannot be generated at the current levels in space. So could there be a time in the past that there were adequate levels? No, I can only give you my thought on this, and I have some experience with vacuum. I worked with vacuum for 15 years. Okay. And I can only tell you my experience. You go into a vacuum chamber and you have a certain volume, you have atmospheric pressure to start out with. Now you pump down the system with a couple of pumps in series. First you pump it down with a mechanical or rotary vane pump. And then you you attach it to either a diffusion pump or a cryo pump. Those are the typical ones. They have other turbo pumps and so on. And then you can pump the chamber down, that volume, down to, we usually worked at the -7 torr range. What does that mean? It means you pulled particles out of the system. You pulled atoms out of there. You have less volume of particles and more volume of something called empty space, or a nothing called empty space. And this was the argument that Torricelli and von Guericke and Robert Boyle, they all said, look, I pumped the chamber down, whatever device they had there, they pumped it down. They said, what's left in there if I pumped all the particles out of there? And the argument of people like Hobbes or even Descartes was that particles of ether seeped in through the interstices and occupied the volume where the atoms that you pulled out were. That was their answer. So they said there is no such thing as empty space. Because whenever you remove something, something else takes its place. That's the logic that they had. And so they never answered the question that I would ask them, is what surrounds each particle? What gives shape to each particle of ether? That's what we got to answer. Why does it have a surface? What serves as a contrast, as a backdrop? And so, when you pump down a chamber, you're removing particles, and what remains in there is known as vacuum or space or nothing. And when you go into outer space You go to the moon, you get down to minus 11, minus 12 torr level. It's, we have a hard time achieving those vacuum levels here on Earth. Very hard time. Yeah, it's very hard to achieve that here. But on the moon, it's normal. That's the normal environment. In fact, the solar wind is in the minus 12, minus 13 range. And so there's nothing there, essentially. You don't have a plasma to do electricity. And that's the issue. The issue, if you worked with plasma like I did, I hate to say it, but yeah, I worked with so-called plasma, right? Yeah, we could run an electric current because we were working at the minus 3 torr level. You pump down the chamber to minus 7, right? You have a good vacuum, a stable vacuum. Now the first thing you do is you have to introduce species in there. You have to introduce atoms. What atoms? Inert atoms. We use the argon. So you introduce argon, fill the chamber back up with atoms. You ionize them with electricity, right? Something happens there, some magic, ionize it. What does it mean? Well, under the quantum version, you're removing the electron from the atom. And so now you can play around with them with magnets. You can direct them in one direction or in another. Okay, you can do something with that. That's what you would have to do in outer space. God, if this is God's garage, right? And he's going to create a vacuum. Now he's got to fill it up with argon or any other species for that matter. I'll use just argon as an example. Now you have to ionize it throughout the entire universe. Hopefully it has borders. It's a little box or four-dimensional space-time, whatever. So it's got to be a finite region, okay? You fill it with argon between the galaxies, between the stars, between the sun and the earth. And now you ionize it. Now you can have a current. But first of all, that doesn't exist. There is no certified. There is no minus 3 torr level out there in space. That's the first issue. The other issue is this is something you can show for yourself. Okay, you can prove to yourself. Okay, go buy yourself a plasma ball. Okay, buy yourself a plasma ball and watch it for a little while. Okay, and that's a little volume filled with gas. Okay, that's what it is. And now you tell me, after watching it for a little while, you see all this fancy stuff going on in there. You like it. It's good to create lights and so on. I want you to tell me, okay, if you get a constant current or you get what is known as arcing, you get zaps. You get a zap here, you get another zap there, and another one there, and another one there. Okay, you get all these intermittent zaps and at different locations, and they're not in a straight line. They're all wiggly. It's like lightning here, lightning there. It's intermittent. It's not a constant current. So if you're going to explain, for example, like the electric universe wants to explain gravity in terms of electricity, why the earth is stuck to the sun, why it doesn't fly away. Well, what they have to show is that there's a constant current going from the sun to the earth. You cannot do it with in God's garage, right? You cannot do it with an environment of gas that is ionized and that you have a constant current in one direction only. You know, if God filled his garage with gas and ionized it, you would have a plasma ball. You would have all this arcing in every direction. You would not have a constant current in one direction only that would keep the earth going around in, an elliptical order path around the sun. That's my point. So even if God filled his garage with gas and ionized it, which is not true to begin with, he would have a hard time keeping the earth going at a constant circular or almost circular path around the sun. Okay, so take a look at a plasma ball and you'll see it's arcing. It just wing, 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 just in every direction. It's not constant, it's not a constant current like you would have on a wire. And that's what you would have to have if you're going to explain, gravity in terms of electricity. you would have to have a constant current from the Earth to the Sun or vice versa. And that current would be attractive, okay, fine. And I don't know how that would be, because if you're throwing electrons out, if that's what you think electricity is, a flow of electron beads through all these atoms that are connected from the Earth to the Sun, you have this electron flow from the Sun to the Earth. It's got to be constant. It's got to be perfectly constant, because the Earth doesn't go out and then come back in, and it doesn't zigzag around the Sun. It goes in a smooth fashion around the Sun. How? Like if you twirled the ball at the end of a string. That's how the Earth goes around the Sun. Okay, with that, I'm gonna have to see you again. I'm not gonna be here on Wednesday. I'm on the road, so I'll see you on next Sunday. Okay, and we'll continue with this line of punishment. We'll see you then. Bye bye.